Our planet is a place of constant motion, where massive plates are always shifting, colliding, and pulling apart. These movements drive powerful phenomena like earthquakes, volcanic eruptions, and mountain formation. Nowhere is this more evident than in the Ring of Fire, a zone of intense volcanic and seismic activity, home to 75% of the world's volcanoes and 90% of its earthquakes. Volcanoes, while dangerous, are the lifeblood of our planet. They create fertile soils and shape the Earth's atmosphere and oceans. The Ring of Fire's volcanoes have formed islands like Japan and Indonesia. Eruptions can impact global climate and trigger tsunamis. The Ring of Fire is a testament to nature's power and our planet's dynamism. The Ring of Fire, a zone of intense geological activity, traces the boundaries of the Pacific Ocean basin. It is here, along this nearly continuous arc of volcanoes and earthquake zones, that the Earth's tectonic plates collide and grind against each other, generating immense forces that shape the planet's surface. This volatile region, spanning over 40,000 kilometers, or 25,000 miles, is a testament to the Earth's unceasing internal energy. The Ring of Fire is not a uniform entity. Rather, it is a complex and dynamic system composed of numerous individual segments, each with its own unique geological characteristics. These segments are defined by the specific interactions between the Pacific Plate and the surrounding continental and oceanic plates. The Pacific Plate, one of the largest tectonic plates on Earth, is in constant motion, moving at an average rate of a few centimeters per year. This movement, while seemingly insignificant on a human timescale, has profound consequences over geological time, leading to the formation of volcanoes, mountain ranges, and deep ocean trenches. The Ring of Fire owes its existence to the process of plate tectonics, a fundamental theory that explains the Earth's dynamic surface. According to plate tectonics, the Earth's outermost layer, the lithosphere, is divided into a number of rigid plates that move and interact with each other. These plates, composed of the Earth's crust and the uppermost part of the mantle, float on the asthenosphere, a partially molten layer beneath the lithosphere. The asthenosphere's ability to flow slowly allows the tectonic plates to move, albeit at a snail's pace. The plates' interactions give rise to the Earth's most dramatic geological features, including the Ring of Fire. The majority of the volcanoes and earthquakes along the Ring of Fire occur in subduction zones, regions where one tectonic plate slides beneath another. In these zones, the denser plate, which is typically an oceanic plate, dives beneath the lighter plate, which can be either oceanic or continental. As the descending plate plunges into the Earth's mantle, it heats up, releasing fluids that melt the overlying mantle wedge. This molten rock, known as magma, rises towards the surface, erupting to form volcanoes. The subduction process is not smooth. Rather, it is characterized by intense friction and pressure as the plates grind against each other. This immense stress builds up over time and is periodically released in the form of earthquakes, some of which can be incredibly powerful and destructive. The depth at which these earthquakes occur varies depending on the angle of subduction and the physical properties of the plates involved. The Ring of Fire's volatile nature is a testament to the immense forces at work within the Earth. The Pacific Plate's interaction with neighboring plates creates intense geological activity, resulting in frequent earthquakes and volcanic eruptions. This dynamic region highlights Earth's ever-changing nature. Understanding these processes is crucial for mitigating risks. The Ring of Fire is also a region of creation. Volcanic activity forms islands like the Hawaiian and Aleutian Islands. The Ring of Fire, a testament to the Earth's restless nature, is home to a multitude of volcanoes, each with its own unique characteristics and history. From the snow-capped peak of Mount Fuji in Japan to the steaming crater of Mount St. Helens in the United States. These fiery mountains captivate our imaginations and remind us of the immense power that lies beneath the Earth's surface. These volcanoes, scattered across the globe, offer a glimpse into the forces that have shaped our planet for millennia. Their majestic beauty, often shrouded in plumes of smoke and ash, belies the destructive potential they hold. Volcanic eruptions, while capable of causing widespread devastation, are also an integral part of the Earth's natural cycles. They have played a crucial role in shaping our planet's atmosphere, oceans, and continents over billions of years, and they continue to influence our world today. Mount Fuji, Japan's highest and most iconic peak, stands as a symbol of the nation's cultural identity and natural splendor. Rising to an elevation of 3,776 meters, its symmetrical cone has inspired artists, poets, and pilgrims for centuries. Mount Fuji is a sacred site, revered by the Japanese people as a dwelling place of gods and a source of artistic inspiration. Its slopes, covered in lush forests and dotted with serene lakes, attract millions of visitors each year. But beneath its tranquil exterior lies a fiery heart. Mount Fuji is an active stratovolcano, its last eruption occurring in 1707. This eruption, known as the Hoi eruption, blanketed the surrounding region in ash. Despite the risks, Mount Fuji holds a special place in the hearts of the Japanese people. Mount St. Helens, located in the Cascade Range of the Pacific Northwest of the United States, stands as a stark reminder of the devastating power of nature. Once a symmetrical cone-shaped peak, its landscape was forever altered on May 18, 1980, when a massive eruption ripped through its north face. The eruption, the deadliest and most economically destructive volcanic event in U.S. history, reduced the mountain's elevation by over 1,300 feet and left behind a gaping crater. The blast, heard hundreds of miles away, flattened forests, melted glaciers, and triggered mud flows that choked rivers and devastated communities. The eruption of Mount St. Helens serves as a sobering reminder of the importance of understanding and respecting the power of volcanoes. Despite the devastation, Mount St. Helens has shown remarkable resilience. Mount Pinatubo, located on the island of Luzon in the Philippines, lay dormant for centuries, its slopes cloaked in dense forests. However, in 1991, it awakened with a fury that shocked the world. The eruption of Mount Pinatubo was one of the most powerful volcanic eruptions of the 20th century, ejecting millions of tons of ash and sulfur dioxide into the atmosphere. The eruption had a global impact, causing a temporary cooling effect on the Earth's climate. The ash cloud from the eruption circled the globe, reducing global temperatures by an average of 0.5 degrees Celsius, or 0.9 degrees Fahrenheit, for several years. The eruption of Mount Pinatubo highlighted the interconnectedness of our planet and the far-reaching consequences of volcanic activity. It also underscored the importance of monitoring volcanoes and developing effective early warning systems to mitigate the risks posed by these powerful natural phenomena. The Earth's fiery breath understanding volcanic activity. Volcanoes, often perceived as fiery mountains of destruction, are in reality windows into the Earth's fiery heart. They provide us with a glimpse into the immense forces that shape our planet from deep within. Volcanic activity, though potentially destructive, is a fundamental geological process that has been shaping Earth's surface for billions of years. It is a testament to the Earth's internal heat and the constant movement of its tectonic plates. To understand volcanoes, we must first delve into the Earth's structure. Beneath the Earth's crust, which is broken into a mosaic of tectonic plates, lies the mantle, a layer of hot, mostly solid rock approximately 2,900 kilometers, or 1,800 miles, thick. The mantle, though solid, behaves like a very viscous fluid over geological timescales. Within the mantle, temperatures and pressures are immense, high enough to melt rock and form magma. The birth of a volcano, from magma to mountain. Magma, less dense than the surrounding solid rock, rises buoyantly towards the Earth's surface. As magma rises, it can accumulate in underground chambers called magma chambers. Over time, the pressure within these chambers builds, and when the pressure exceeds the strength of the surrounding rocks, the magma is forced upwards through cracks and fissures in the Earth's crust. This molten rock, upon reaching the surface, is called lava. The eruption of lava, along with ash, gases, and volcanic debris, leads to the formation of a volcanic edifice. The shape and size of a volcano depend on several factors, including the composition of the magma, the rate of eruption, and the surrounding topography. Volcanoes are not all alike. They vary widely in shape, size, and eruptive style, reflecting the diversity of geological processes that create them. A spectrum of eruptions, from gentle flows to explosive blasts. Volcanic eruptions are not all catastrophic events. They can range from relatively gentle outpourings of lava, known as effusive eruptions, to violent explosions that eject ash and gas high into the atmosphere, known as explosive eruptions. The type of eruption depends largely on the viscosity of the magma, which in turn is influenced by its silica content and temperature. Magma, with a high silica content, tends to be more viscous, trapping gases and leading to a buildup of pressure that can result in explosive eruptions. On the other hand, magma with a low silica content is less viscous, allowing gases to escape more readily and resulting in more effusive eruptions characterized by lava flows. Understanding the different types of volcanic eruptions is crucial for assessing the hazards associated with each and for developing effective mitigation strategies. Section 4. The Science of Prediction, Monitoring Earth's Pulse. Predicting volcanic eruptions with absolute certainty remains a challenge, but scientists have made significant strides in understanding the signs that precede an eruption. Volcano monitoring involves a multifaceted approach, employing a suite of instruments and techniques to track changes in a volcano's behavior. Seismometers are used to detect earthquakes, which often increase in frequency and intensity before an eruption as magma rises through the crust. Ground deformation, or changes in the shape of the volcano, can be measured using tiltmeters, GPS receivers, and satellite-based radar, providing insights into the movement of magma beneath the surface. Gas emissions from volcanoes, such as sulfur dioxide and carbon dioxide, are also monitored, as changes in their composition and flux can signal an impending eruption. Section 1. Nature's Fury Unleashed, the Impact of Volcanic Eruptions. Volcanic eruptions display Earth's raw power, with lava flows and pyroclastic currents obliterating landscapes. Ash clouds disrupt life, collapsing roofs and posing respiratory hazards. The 1980 Mount Street. Helen's eruption leveled forests and triggered devastating mud flows. Section 2. A delicate balance, volcanic eruptions and the environment. Volcanic eruptions can have long-lasting impacts on the environment. Ash and gases can disrupt weather patterns and affect global climate. Sulfur dioxide forms aerosols reflecting sunlight and cooling the Earth. The 1991 Mount Pinatubo eruption caused significant global cooling. This reduced global temperatures by about 0.5 degrees Celsius. Eruptions impact ecosystems, smothering vegetation and contaminating water. Acid rain from eruptions can harm aquatic life. Section 3. A double-edged sword, the human toll of volcanic events. Volcanic eruptions pose significant risks to human societies, particularly those located near active volcanoes. Immediate hazards like lava flows, pyroclastic flows, ashfall, and gases cause destruction and displacement. The 79 AD eruption of Mount Vesuvius buried Pompeii and Herculaneum, killing thousands. Many were entombed in ash, their remains preserved for centuries. Modern eruptions still challenge disaster preparedness and response. The 2010 Eyjafjallajökull eruption disrupted air travel across Europe. Section 4. Lessons etched in ash. Historical eruptions and their impacts. Volcanic eruptions have shaped human civilization, leaving a legacy in ash and stone. The Thera eruption around 1600 BC devastated the Minoan civilization. Massive tsunamis from the eruption contributed to the Minoan decline. The 1815 Mount Tambora eruption caused a volcanic winter, leading to famine. Krakatoa's 1883 eruption generated tsunamis, killing 36,000 people. Section 1. Guardians of the Earth. Monitoring volcanic fury. As our understanding of volcanoes has grown, so too has our ability to monitor these fiery giants and anticipate their eruptions. Scientists around the world work tirelessly, using a range of sophisticated instruments and techniques to keep a watchful eye on active volcanoes, especially those located in densely populated areas. Their work is crucial for mitigating the risks associated with volcanic eruptions and for ensuring the safety of communities living in the shadow of these volatile mountains. Volcano monitoring is a multidisciplinary endeavor, drawing on expertise from various fields including geology, geophysics, geochemistry, and remote sensing. By studying the subtle changes in a volcano's behavior, scientists can detect signs of unrest, such as increased seismic activity, ground deformation, changes in gas emissions, and variations in heat flow that may indicate an impending eruption. Technological advancements have revolutionized the field of volcano monitoring, providing scientists with unprecedented capabilities to observe and interpret the subtle cues of an awakening volcano. Seismometers, highly sensitive instruments that detect ground vibrations, are deployed around volcanoes to monitor for earthquakes, which often increase in frequency and intensity as magma rises through the Earth's crust. Tiltmeters and GPS receivers are used to measure ground deformation, or changes in the shape of the volcano, providing insights into the movement of magma beneath the surface. Spectrometers deployed on the ground or mounted on aircraft and satellites analyze the composition of volcanic gases, such as sulfur dioxide, carbon dioxide, and water vapor, providing clues about the magma's movement and potential for eruption. Thermal imaging cameras and infrared sensors detect changes in heat flow, which can indicate the presence of magma near the surface. The importance of preparedness, saving lives before disaster strikes. Effective volcano monitoring is only one part of the equation when it comes to mitigating the risks associated with volcanic eruptions. Equally important is the development and implementation of comprehensive volcano hazard assessments, early warning systems, and evacuation plans. Volcano hazard assessments involve identifying areas potentially at risk from various volcanic hazards, such as lava flows, pyroclastic flows, ashfall, and lahars, based on a volcano's past eruptive history, topography, and prevailing wind patterns. Early warning systems based on real-time monitoring data and hazard assessments are crucial for providing timely alerts to communities in the path of potential volcanic hazards. These systems rely on a network of sensors, communication infrastructure, and trained personnel to disseminate warnings effectively and efficiently. A global effort. Sharing knowledge and resources. Volcano monitoring and risk mitigation are not just national endeavors. They require international cooperation and collaboration. Many volcanoes are located in remote or politically unstable regions, making it challenging for individual nations to monitor and respond to volcanic crises effectively. International organizations, such as the World Organization of Volcano Observatories, play a vital role in facilitating the exchange of scientific knowledge, data, and best practices among volcano observatories worldwide. They also provide training and capacity-building support to developing countries to strengthen their volcano monitoring and risk reduction capabilities. The global effort to monitor volcanoes and mitigate their risks is a testament to the shared responsibility we have in protecting lives and livelihoods from these powerful forces of nature. Respecting nature's power. The Ring of Fire, a fiery necklace adorning the Pacific Ocean, stands as a testament to the awe-inspiring power of our planet. It is a zone of constant creation and destruction, where tectonic plates collide and grind against each other, giving birth to fiery mountains and triggering earth-shattering tremors. The volcanoes that dot this volatile region, from the iconic slopes of Mount Fuji to the smoldering crater of Mount St. Helens, remind us of the immense forces that shape our world from deep within. While these fiery giants can unleash devastation upon the Earth and its inhabitants, they also play a vital role in the planet's delicate balance. Volcanic eruptions, though potentially destructive, enrich the soil, shape continents, and influence global climate patterns. They are a reminder that we are but temporary residents on a planet that operates on its own timescale, driven by forces far beyond our control. A call to action protecting our future. As we marvel at the Ring of Fire's splendor, we must acknowledge our responsibility. Advances in monitoring and early warning systems help mitigate volcanic risks. Continued research and collaboration are essential to protect lives and understand our dynamic planet.